All right, so we need to do a piecewise graph. Piecewise graph means part of our graph is going to be on the left-hand side or right side. Sometimes it's in the middle, depending on how many of these we have. Well, we have two graphs. We have the graph y equals negative x, and we have the graph y equals x plus 1. If I would graph both of those would be two lines on top of each other, which wouldn't be a function. So in order to make it a piecewise function, we said, well, when x is a specific value, we're going to graph something. And when it's a different value, we're going to graph something else. So I always, we have x is less than 0 and x is greater than or equal to 0. So I would put a line at x equals 0 and let myself know that that line is basically the wall between two graphs. Well, the left-hand side is where x is less than 0. The right-hand side would be where x is greater than 0. Well, let's start with the left-hand side. I want to know what happens when x is less than 0. Well, that's this top one. That's this top one right here. It says make sure remember, this is really just saying is y equals negative x. I just need to graph y equals negative x whenever x is less than 0. I'm also going to note that it's strictly less than. So this will not have a closed dot. It will have an open dot when it gets to this wall area. All right, so if I'm plotting some values for that, well, let's see. If I plug in a negative 1, we're going to get a positive 1 out. If I plug in a negative 2, we'll get a positive 2 out. If I plug a 0 in, I'll get a 0 in. So you should have drawn this line as my left-hand side. In fact, that's all you would have had to done. No, it works for that one is A. So A is our correct answer. Let's finish off, though. On the right-hand side, I am supposed to graph x plus 1. So I'm supposed to graph this x plus 1. I'm also going to note it's greater than or equal to, so I'm going to put a closed dot when it starts on this kind of dashed line. So when I plug 0 in, because 0 is the dashed line, I would get 0 plus 1, which would be 1 out. So I'd have a closed dot at 1. When I plug a 1 in, we'd have 1 plus 1, which would be 2. When I plug 2 in, I get 2 plus 1, which equals 3. So we'd end up with this closed dot and a line that goes in that direction, which further confirms A would have been your correct answer. A would have been the correct one on that one. All right, next thing we're going to do is questions from the homework. What was that piecewise function one? So that would be 2.2b. Yeah, Chris. 61. Um, 61 is asking you to graph. Oh, let's go ahead and write it down. So they're saying f of x equals square root of 9 minus x squared. Well, there's a couple ways you can tackle this. Eventually, you have to recognize that this is a circle, or at least part of a circle. We can't have negatives in here. Negatives don't work in here, which means my x has to be somewhere between negative 3, because negative 3 squared is 9, 9 minus 9 is 0, and 3. Anything bigger or smaller is not going to work. If I plug a 4 in for this, I'd have 4 squared, which is 16. 9 minus 16, that's going to be a negative number. If this is a negative 4, that also isn't going to work, because negative 4 squared is 16. 9 minus 16 is also a negative number. So it's somewhere between negative 3 and 3. If you would just plug in points and plot it, you'll actually get this graph. If you just recognize that it has to go from negative 3 to 3 and you plot those points, you'll actually get this graph. In fact, you could have just plotted points. You could have plotted negative 4 and found out it didn't work. It'd be undefined. And just pick numbers that work. I think a slightly smarter way to deal with this is recognize that it is, in fact, a circle. Because we could think of this as being y equals the square root of 9 minus x squared. Well, if I squared both sides, we'd end up with y squared equals 9 minus x squared. And we'd end up with x squared plus y squared equals 9. So this is half a circle, because it's not plus or minus. It's just the positive portion of it. And it also, that 9 is going to be your radius squared. So 3 squared, where 3 is your radius. So this would just be a circle that's centered at the origin. So our center is here, and it has a radius of 3, so it would go up 3, it would go right 3, and it would go left 3, and it would be this graph here. And it would just be half of it, because it's just the positive portion of your circle. If I would write negative square root of 9 minus x squared, this would be flipped. If I said positive and negative, then you would have the full circle. So we do not have the full circle. We do not have the full circle. This is actually a function. This is something you could plug in your calculator and check. It is a function. It's just the top of it. All right, other questions? Oh.
37.
Say that again?
37.
37. Uh, 37 says we're going to do square root of x plus 2 whenever x is between negative 2 and 2. And it says we're going to do 4 minus x whenever x is greater than 2. So let's go ahead and write that down. So we have f of x goes to two different places. It either is square root of x plus 2 when negative 2 less than or equal to x is less than or equal to 2. So when I graph this line, or this graph, I'm going to know I'm going to use closed dots on both ends because they're both equal to signs. Then we're going to do 4 minus x whenever x is greater than 2. So this is going to be more of a quick sketch than anything else. So if I have my x, y coordinates, we'll go there. Let's know that we have at negative 2 and 2 is where we kind of have the changeover. So I'll make sure I have those marked. We'll have 3, 4, I guess 5, 1, negative 1. Let's go 1, 2, 3, negative 1, negative 2, negative 3. So recognizing that our changeover points are at 2 and negative 2, I'm going to put a vertical line at negative 2. I'll put a vertical line at 2. Between negative 2 and 2, I'm graphing square root of x plus 2. Well, it's always a good idea to pick a starting point here and an ending point here, and then maybe a point in between, so we can kind of see what the graph looks like. So if I pick negative 2 and I plug that in there, well, negative 2 plus 2 is 0. Square root of 0 is 0. And since we do have a bunch of equal to signs, I would put a closed dot there.
Yep, sounds good.
You good?
Yep.
Okay. Yeah.
Thank you.
Yeah. It ended up being something like this. Yeah, for that middle part. All right. Other questions? And I do believe this would attach and go down like that. It would look something like that. Yeah.
69.
69. 69 says you have to come up with an equation for that graph, right? So what I'm kind of looking at is, let me take a picture of it, and then I'll erase my answer real quick, and we'll talk about how I got it. So let's pretend we don't have an answer there. This is how I'm going to start this. I'm going to look at, so that's an open dot and a closed dot. This is where the two graphs switch over. I go from one graph to another graph at x equals a negative 1. And I know I have two graphs. So the starting off of this problem is really, because we're going backwards, I'm going to go, well, okay, f of x is going to be two equations. I don't know the first equation, so we'll say 4, and the next equation is going to be 4. I'm going to put some equation for some interval, some equation for some interval. Well, the big changeover is right here at x equals a negative 1. So let's look at the graph that goes left of it. I'm looking at whenever, so if I'm looking at this side of it, so in fact, let's put a dashed line like we would if I was graphing it. The left-hand side is where x is less than 0. The right-hand side is where x is greater than 0. All right, let's handle that x is less than 0. So I'm going to graph this line whenever x is less than 0, and note the open dot. I'm not going to put an equal to sign, so I'm actually going to come up here. I'm going to put for x is less than 0. No equal to sign because it's not a closed dot. Now for when x is greater than 0, notice the closed dot. So I'm going to go ahead and put x is greater than or equal to, I'm not 0. I should have been -1. I'm sorry. X is greater than or equal to a -1. We should have had a -1 there, not a 0. So that should be when x is less than -1 and where x is greater than -1. And so that one should also been x is. Uh-oh, using the wrong one. This should be where x is less than a -1, and x is greater than or equal to -1. Do all those values make sense now?
Yeah.
Okay, so that's the start of this. Now we just need an equation for this line. We just need an equation for this line, and if we look at this line, it's going to go through the y-intercept if I continue at kind of that 0 there. Did I have the wrong equation for this one? I'm just looking at it. And so I have the point -1, 1, 2, 2. So that should have been just -x, right? Is that what I had for my answer? Oh, I did. Okay, yeah, we're fine. Okay, we're fine. I thought I had a different answer for that one. Yeah, so this one is just -x. It just comes right here. This one has a slope of 1, and it goes through our y-intercept at -1. So it has a slope of 1, so it'll be just x minus 1 for that equation for that one. You could have put it into point slope and came up with an equation that way. But I would just, it intercepts at -1, so we have -1, and it has a slope of 1, 1. Okay? Other questions? Yeah?
For that problem still, did you say absolute value of x instead of -x?
Yeah.
Good.
Yeah. Because the absolute value of x, we can't see the other side of it, so it could have bounced and gone that way. Yep. Absolute value of x would actually work for that one, yeah. Other questions? Okay, then today we're actually going to cover something we've already covered before. That is transformations of parent functions. We did this before when we were doing our sine and cosine graphs. So today we're just going to talk about what happens when a graph shifts left, right, up, down, it flips, it stretches, it shrinks, that kind of stuff. And it's going to go pretty quick because we've already talked about this before. All right, the first thing we're going to talk about is a vertical translation. That is a graph being shifted up or down. Now, to shift something up or down, let's just go ahead and go. I think I used f of x. I just want to keep them all the same. Yeah. So if you have f of x and you add a number to it, say we have x squared like we have down here. If you add a number to a parent function, it's going to get shifted up. If you have a parent function and you subtract a number, it is going to be shifted down. So for our example down below, we're supposed to graph g of x equals x squared plus 2, and we're supposed to graph x squared minus 3. Well, our parent function is going to be x squared. So I'm talking about f of x equaling x squared is my parent function, and those two are going to be kind of the offshoots. It'll be our sibling functions. So I did graph x squared for you. Because once you know the graph of x squared, shifting it up 2 or down 3 isn't going to be that hard. So when I'm graphing g of x, I'm just going to shift all of the points up 2. So it's going to look something like this. Shift all of your points up 2. And we'd have something that looks like that. And that blue graph is just our g of x. It is up 2. Then down 3 is just shifting all of our points down 3. So rather than being at 0, 0, we're going to have at 0, negative 3. Instead of being at 1, 1, we are going to be at 1, negative 2 on both sides. And so our parent function being x squared shifted down 3. This will be my h of x. Let's make that better. That is if you were adding or subtracting outside of the parent function. To shift it left or right, you are going to add or subtract inside your parent function. So I changed my input to x plus 2 rather than it just being x squared. So if you are adding or subtracting inside, that would look something like this. F of x plus k. If you're adding inside, it's going to go the opposite direction you think. F of x plus a number is actually going to go left. That will make it go left. When I subtract a number inside the function, so I have f of x minus k, that is going to go right. Once again, my parent function is x squared. So I'm changing my input to, instead of being x squared, I'm making it x plus 2 squared. I'm inputting x plus 2 and seeing what I get out. So we are changing our input. It's happening inside of our parent function. So if I needed to do x plus 2 squared, I would just first graph x squared, and then I would shift everything left 2. So we'd go left 2 for that point. We'd go left 2 for this point. We go left 2 for that point, and that's probably all we needed to do that. So that is our left 2, and that becomes our g of x. Our other one is subtracting 3 inside of our parent function. Rather than x squared, I have x minus 3 squared. So we are going to move right 3. A negative 3 on the inside actually moves it right 3. So we're going to move all of our points right 3. And we're going to do something like that. On the test, you have to know how to do these. All right, there's just not enough time for you to plot all of the graphs that you need to. If you look at your homework's going to go really, really quick. If you know what a parent function is, and you know if you're going up, down, left, right. If you don't know what's happening, you have to plot every single point, your homework's going to take a long time. All right, the next two things we're going to talk about are reflections. Reflections across the x-axis and reflections across the y-axis. I don't know what all my slides are. There we go. All right, we're going to go across the x-axis, and then we're going to go across the y-axis. To flip across the x-axis, if you have a negative side on the outside of your function, so on the outside of it, so note my parent function here was absolute value of x. I'm putting a negative on the outside. If you have a negative on the outside of your parent function, you're going to reflect across the x-axis. So your big thing, if you have a negative on the outside, you're looking at your x-axis, which I'm marking in blue right now. So that is your x-axis. I'm just marking it because it's kind of small there. So you're going to take all of your points and you are going to reflect them across the x-axis, which will look like this. If I have this point and I go across the x-axis, we'll have there. If I take this point and go across the x-axis, we're going to have, I didn't go far enough. We're going to come down here. And at the end of the day, you're going to have a mirror image going across the x-axis. That red one becomes my g of x. That is if you have a negative on the outside of your parent function. If you have a negative on the inside of your parent function. So note, my parent function here would be square root of x. If it was negative square root of x, I reflect it across the x-axis. However, this is square root of negative x. The negative's on the inside. If the negative's on the inside, you then reflect across the y-axis. Once again, a negative on the inside of your parent function goes across your y-axis. So in this case, no longer looking at the x, I'm looking at that vertical line there, and I'm saying, okay, I'm going to reflect all of my points across here. So I'm going to go way over here. And so I'd have something that looks like a mirror image across my y-axis. Be careful with these. Once again, on the outside, you're reflecting across your x-axis. If your negative is on the inside of your parent function, you will cross the y-axis. So example of that, these are good examples. We have one on the outside, x, inside, y. Those are the easiest ones to get confused. All right, the next thing we are going to talk about are vertical stretch and vertical shrinks. All right, vertical stretch. Vertical stretch is just what it sounds like. You are getting skinnier and skinnier as you stretch it out vertically. So our vertical stretch is going to be anytime we have a value out in front of our parent function, let's call it a. So if I have a times f of x, you are going to have a vertical stretch anytime, where your absolute value of a is bigger than 1. That just means nothing between 1 and negative 1. Those will actually turn into shrinks. So when this a value is bigger than 1, so think 2, 3, 4, 5, 6, 7, or negative 2, 3, 4, 5, 6, 7. They can be negative. As long as the absolute value is bigger than 1, it is going to be a stretch. When a is negative, it's just going to flip across your x-axis and then stretch. All right. So my example here is if I have 2 times the absolute value of x. So down here I have the parent function, absolute value of x. We're going to do a vertical stretch. So what happens is all of your points get stretched by a factor of 2. So in fact, you're multiplying all of your points by 2. So if we look at this point, which is 1, 1. A vertical stretch is going to multiply that by 2. Just the y value. So the stretched out point will be 1, 2. Let's pick another point. I'm going to pick the point 3, 3. The stretched version of that, you're going to multiply your y value by 2. So rather than being 3, 3, we're going to then have 3, 6. Once again, that 6 comes from the scale factor being 2 times 3. What's that last point? I can't do the last point because we'd be all the way up to 12. I guess we could simulate it. If I pick this point here, that is 4, 4. My stretched out point would be 4, 12, which would be somewhere up here. Probably not the best. Let's just leave it as is because that's going to get way off and get messy. But anyway, when we connect these points, we're going to have a skinnier and skinnier line. And the same thing's going to happen on this side. We'll have a skinnier and skinnier line. So it pulls all of the points up by a scale factor of 2. Oh, no. What was I saying? That would have been 4, 8, right? We could plot that. I didn't realize I had this up here. That would be 4, 8 would be the other point. So we multiply our y values by our scale factor. Vertical shrink is going to be the exact same thing, except now we have a smaller value. We have a smaller value, so it's going to be a vertical shrink. It's still going to look the same. It's where a times f of x, but a is going to be a smaller value. So the absolute value of a is going to be less than 1. So our example is 1/2. Now we're going to take all of our y values and multiply by 1/2. So if I have this point 1, 1, this is the point 1, 1, my shrunk form would then be 1/2. If I pick a different point, if I pick this 2, 4, and I multiply the y value by 1/2, we are going to have 2, 2. And we'd have the same thing happening on the other side. So when you have a vertical shrink, it actually compresses your graph down. It gets flatter and flatter and flatter. A stretch pulls it tighter and tighter and tighter in. I do want to point out a huge fact that people make mistakes on. Did my origin point 0, 0 move? No. And that's because you're multiplying your y value by 2 1/2. 0, 0, 0 times 2 or 0 times 1/2 is still 0. If your graph is centered at the origin, where your y value equals 0, you will not move that point. All the other points are going to shift it up because you're multiplying your y value by a number. If your y value is at 0, it's going to stay put there. And the way I think about it, in order to stretch and shrink, you grab this point down here and you actually pull it up to stretch it up. Here you grab this point and you push everything down. So your origin point is not going to move. All the other points are going to get skinnier because it's getting stretched out, but you're holding your base here and pulling up here. So don't move that origin point when you're doing a shrink or a stretch. That point only moves if you're going left, right, or up or down. All right? The point 0, 0 will never move unless you're going left, right, up, or down. It doesn't move when you are stretching or shrinking. All right, the last thing we're going to do is just one where we do a bunch all in a row. So we are talking about this guy, multiple transformations. With multiple transformations, you're going to graph a function involving more than one transformation in the following order. You're going to do your horizontal translation first. You're going to do your stretching or shrinking. You're going to do your reflection. And the last thing you are going to do is your vertical translation. So the last thing you are going to do is move your graph up or down. In fact, you can do all of these out of order. The only one you have to do last is your vertical translation. And why we don't do the vertical translation first is because of this fact. As soon as you start moving left, right, up and stuff, your point is no longer at the origin, and you really have to think about that origin point not moving. So always do your vertical up and down last, and it's because of your vertical stretch and shrink will be thrown off if you do it before your vertical stretch or shrink. So the last thing you're ever going to do is your vertical translation. You will increase your graphing ability by like 100% as long as you do this last. If you move it in there, you're going to make mistakes. So do your vertical translation last. All right, let's go ahead and do this final graph together. So we need to graph 4 minus 2 times the quantity square root x plus 2. All right, let's first graph the parent function. Our parent function would just be 0, 0, 1, 1, and then 4, 2. When I plug in 4, I get out 2. That is your parent function of your square root of x. All right, I'm going to do my left or right first. So we have x plus 1. If it's inside, it tells you that is going to be your left or right. Does plus 1 make it go left, or does it make it go right? Yeah, it's going to go left. Yep. So because of that plus 1, we're going to go left 1. So let's do that in blue. So we're going to go, all the points are left 1. That is my first graph, and that is my square root of x plus 1. All right, I'm going to go ahead and put that on the next graph too, so we can see what's going to happen to it. We'll leave it the same. And that is my, once again, that is my square root of x plus 1 is left 1. All right, we're going to do two things at once here. Well, we'll put two things in the same graph. The first thing we're going to do is we are going to go ahead and we are going to do our vertical stretching or shrinking. So note that we have a 2 out front. That 2 out front tells me it's going to be a stretch. A stretch means I'm going to multiply all my y values by 2. So let's look at this point right here. This point is negative 1, 0. What's 0 times 2? 0. We're not going to move that. That is centered right here. So a stretch of a point negative 1, 0 is still negative 1, 0. That point is going to remain. Let's go ahead and do this in brown. Our next point is 0, 1. I'm going to multiply my y value to get that stretch. That'd be 1 times 2. So my stretched point would be this point here, 0, 2. Remember that 2 comes from the 1 times 2. Our next point is that 3, 2. You multiply the y value by 2 and you come up with 3, 4. Once again, that 4 is because your stretch is 2. We take all our y values and multiply by 2. And so that is my graph of quantity 2 square root of x plus 1. But I said we're going to do another thing in this one. We're also going to do that negative out front. If there's a negative out front, it reflects across the x-axis. So that negative right there is going to reflect across the x-axis. So you're going to take all of these points that we did up here and we're going to reflect them down here. Once again, your origin point isn't going to move because there's no way to reflect that across the x-axis. This point, however, is going to come down to, rather than being 0, 2, it's going to be 0, negative 2. And then that point 3, 4 is going to turn to 3, negative 4. So that was basically 2 moves in 1. We now have negative 2 square root of x plus 1. I'm going to write that on my next slide as well, or my next graph. And the very last thing I need to do is change this color to green. We have that 4. Note that is adding 4 on the outside of the equation. If you're adding 4 on the outside of the equation, that's going to make it go up 4. So that means we're going to shift all of our points up 4. 1, 2, 3, 4 will be up here. 1, 2, 3, 4 up here. 1, 2, 3, 4 would be here. That green one I'm drawing right now would be our final graph. That was 4 minus 2 square root of x plus 1. That is shifted left 1. It is stretched, it is flipped, and is moved up 4. Now, you might not be able to check every point being correct, but you can at least make sure it makes sense with this. Is it left? Yeah, it's left. Is it stretched? Yeah, it's pulled stretched. Is it flipped? Our square root used to go that way. Yeah, it's flipped. Is it up? Yeah, it's up. At least it looks like it matches everything that's said in here. At least on a test, you would know that you did all your moves right. Maybe you moved left 2 instead of 1 or something like that. But in general, you should be able to see that the shape of your graph matches what is described up here, which it is. Now, I did draw basically every single step of this. Are you going to do that every single time? Probably not. Can you? Absolutely. If you need scratch paper and you're on a test or something like that, just ask for it. You can graph every single step if that helps you get it correct. I do encourage you at times to combine steps. Like this one, I just put the points up here and then I reflected down here. So I didn't waste the time graphing that brown one. I'm just like, okay, I know those are going to be reflected down there. It saves you some time combining steps. All right, any questions on parent function transformations? I know this seems like a long lesson because it is 3 pages, but realistically, these are just all your parent functions in case you don't know what a parent function looks like. It can save you time. You should know what all of these are. They're the basics, just y equals 4. The other one is just y equals x. Then we have just a slope of 3 up 2. We have the absolute value. We have x squared. We have the square root of x. We have a cube function. We have a cube root function. And finally, we have the greatest integer function. Those are your major parent functions that you should know. Also, the question that Chris brought up, that is something you should know for this too. What does the equation of a circle look like if it's a function? Meaning, what equation do you have if it's just the top of the circle? And that is just that square root of 9 minus x squared that we talked about before. All right, this homework shouldn't take you that long. It is just moving from parent function. Most of them are basically just one moves. They're like, just show me you can stretch, show me you can shrink. I think maybe the hardest ones are 25 through 33 because they tell you a description of your graph, and you actually have to come up with the equation for it. Those are probably your hardest ones.